James, thank you so much for joining us today. So everyone, welcome to the Planetary Science Sample Seminar Series, or as we like to call it, again, it's sponsored by Survey, LPI, the UNM Grand Challenge, RASL, and of course it's hosted here at UNM with the Institute of Meteoritics. So good morning to everybody here on the west of the Mississippi, good afternoon to everyone on the east of the Mississippi, and potentially good evening to people across the pond from us. But we are super excited today to have James from Jet Propulsion Laboratory giving us a talk. And so, James, please take it away.
Okay, again, sorry for the technical difficulties. I'll take blame on it. Actually, I'll defer the blame. One of the reasons I'm busy today is Jack Schmidt is visiting JPL. He's just down the hallway. So I'll blame the Apollo astronaut. But I won't be able to see, I can't see any of you or see the chat as this is going on. So please interrupt me if there are pressing questions. But yeah, I'm here to talk about endurance. I am the JPL Endurance Science Lead. I've had the privilege of championing this concept since its inception in the Decadal Survey, and I'm currently supporting the recently announced science definition team for SPARCS, the South Pole-Aitken Basin Sample Return and Exploration Mission, which is going to be really important for shaping this concept. So, at a quick glance, what is endurance? Endurance is a long-range rover concept designed to traverse and collect samples from across the South Pole-Aitken Basin on the lunar far side. And it's a science mission. It is motivated by long-standing questions we've had about the moon, about the solar system, and getting those samples from SPA has been the highest priority for lunar science for decades now. And it was really exciting when the Decadal Survey recommended this mission for implementation to, in my mind, finally get this thing done. Make sure that we're getting those samples and answering those questions as quickly as we can. So endurance was recommended as a strategic mission in the next decade as the highest priority for the Lunar Discovery and Exploration Program. So for those of you that speak NASA org chart, that's Joel Kearns' program within SEO. So it's sort of parallel to the usual Planetary Science Directorate. So the way I structured this talk, which I'll adjust based on time, is to really first start with why South Pole-Aitken Basin, and then the mission concept and the next steps for endurance. So this mission is going to the far side of the moon. So this is the view of the moon we're all familiar with. This is a lovely visualization from Goddard, from their science visualization studio. And here in a sec, we're going to swing on to the far side of the moon, which looks notably different. And in a sec, you'll also see the Earth pop into view as we're stationed on this hypothetical far side observer. And the far side of the moon looks very different. It has different geology, it has older, rougher, more cratered terrain. And a particular notice, if you look at the southern part of the far side, you see the slightly dark region. That is South Pole-Aitken Basin. And it does not really pop in visible or color imagery, but it does when you start looking at topography and other geophysical data sets. So here's that same sort of hyper color view of the far side. SPA really pops in topography. So this is Lola topography. And immediately you see this enormous basin. It's over 2,000 kilometers across. Depending on how you define your reference frames, it's something like 8 to 10 kilometers deep. This is the largest undisputed impact basin on the moon. It is also the oldest. So, and here's just this, I've been showing a lot of visualizations. This is a real image taken from an Earth observing spacecraft. And every once in a while, the moon photobombs this, its lovely view of the Earth. And I just love this image so much because it helps contextualize the moon. But you can see South Pole-Aitken down here. So, I'm gonna move this. Oops. So this basin is enormous. These are two simulations, 3D simulations of the impact itself. The left is an iCell simulation by Jordan Kendall that was published by the late Jay Milosh. On the right is a CTH model by Citron et al. That came out just last year. So this basin would have been a planetesimal sized object, something maybe 100 or 200 kilometers across, smacking into the moon at high velocity. It almost certainly excavated lower crust and mantle material, although we still to this day debate where that material is on the moon and its exact composition. You can see that on the right. Here, this tan material is material that they ascribe to as lunar mantle material. You can see it just sort of splashes onto the far side. On the left, the colors correspond to temperature, and the impact is violent, and you expect melting in some central part of the basin. SPA is geologically diverse, and you could have entire lectures just about the geology of South Pole-Aitken Basin. Here I show some of my favorite maps made by Dan Moriarty, who studied the basin extensively. And so while we want to know these sort of big picture questions like what's the age of the basin and is there mantle material there, we have to take into account how diverse this is, the varied terrains in there, and the very complicated geologic history that they are telling us about this basin. So it makes it hard to go there and know that you've gotten the right landing site or the right samples to really answer all these questions. For the sake of time, I'm going to skip these. SPA is so large that it may have had global ramifications for the moon. And so over the years, there have been a variety of hypotheses proposing that the SPA impact may be tied to broader lunar geophysics. And in particular, on this page, I'm showing 3 different papers from different authors, effectively arguing that SPA may have affected the near side of the moon. The near side is, of course, dominated by volcanic terrains. It's very complex. It has very unusual tectonics, like this giant square that was detected by Grail gravity data, and it's geochemically unique, but we don't know exactly why it's unique. There are a lot of theories, and this SPA related hypothesis is an interesting one. In some cases, folks argue that the SPA impact, like this work by Pete Schultz, effectively there were shock waves that moved through the moon and focused their energy onto the far side, fracturing it, maybe melting it. These more recent papers by Zhang and Jones et al. Look at the impact and how it changed the thermal structure of the far side of the moon, and that imparting all that heat sort of destabilizes other parts of the moon. It can cause, for example, downwellings on the near side of the moon. So let's actually play this one. This one's fun. Here, SPA happens in the bottom, and it triggers this destabilization of melt. In this case, it's creep material on the near side. So I get really excited when we talk about impacts and how they might affect planets as a whole. And to that effect, SPA is not unique in the solar system. I would classify it as a mega basin, an impact basin that has a diameter comparable to the size of the planet itself. And we see these all over. Here's Hellas on Mars. Hellas is it has the same physical dimensions roughly as SPA, but there are even bigger basins across the solar system. Things like Caloris. Here I threw in some icy satellites like Turgis on Iapetus, Sputnik on Pluto, one of my favorite basins that I've worked a lot on. Here's SPA. So you can see I've scaled all the planets the same size on the page. Eventually you can get impact basins that are even proportionally larger than SPA, things like the Borealis impact on Mars, which is a hypothesized impact basin that may have formed the north-south dichotomy on Mars. And so as someone who thinks a lot about planetary science beyond the moon, I get really excited thinking about how exploring the closest, most accessible mega basin could be used to ground truth the models that we develop and test on other worlds. And of course, the biggest challenge here is that we just lack samples from SPA. Samples are critical for both determining ages of different geologic events, but also measuring chemistry, which we can use to back out chemistry at depth and all sorts of other fun things. We have, for the first time from Chang'e 6, samples from the Apollo Basin in SPA, but we still have not sampled most of the more interesting, in my opinion, geologic diversity in the center of the basin and other locations within the basin. And I like showing this compared to the near side, where we have, thanks to Apollo and also the Luna missions, and also now Chang'e 5, the value in having samples from a region and building a complete story of that region. And we still argue to this day about the geologic history of Procolarum and what exactly are we dating? Are we always dating Imbrium? Are we dating Crisium, other basins? But that integrated story from a campaign is really important for moving the entire story forward. So for chronology, I'll actually show this again. SPA is the earliest basin that is preserved on the moon. So in this visual, again from Goddard, you see the freezing out of the magma ocean. And the first thing that happens after that in this cartoon is the formation of the SPA impact. So this is the furthest back that we go in lunar chronology that we have great confidence in, but we still don't know exactly when this happened. And figuring out when this basin happens is important for constraining both the things that came before, like the evolution of the magma ocean, and the things that came after. So here you can see this, the so-called late heavy bombardment that is hypothesized, where you have a lot of basin-forming impacts around 3.9, 4 billion years ago. Again, still debated, and the only way to really test these hypotheses is going back and getting samples from the right places. So one way you can sort of visualize this is by building up a chronology of impacts over time. So I'm going to do this sort of piecewise, going from today on the left back to 4.5 billion years ago on the right. And I'm showing the geologic timelines for the moon, Earth, and Mars on the bottom to sort of provide context. So as you go back in time, the number of impacts hitting an object increase. There were more small bodies, they were getting destabilized by various dynamical processes. And a lot of this time frame between 3 and 4 billion years is relatively well constrained by the dated Apollo and Luna terrains, and also Chang'e samples now. But once you get to sort of 3.9 and beyond, you start having diverging models. And a classic example is the late heavy bombardment. Always a hot topic, always a fun session to go to at LPSC to see who's arguing about it. But was there a cataclysm on the moon and on other rocky worlds in the inner solar system triggered by some dynamical destabilization of small bodies? So things like the migration of Jupiter in a so-called Nice model or Grand Tack model. So one way to test this would be to get samples from other large basins, particularly on the far side. We want to get away from the terrains we've sampled before, because we still debate about exactly which basins we're sampling. And going to the far side is one way to mitigate that. As you go even further back in time, the number of models become far more numerous, far less constrained, because we don't have dated terrains at this age. And this is the domain of SPA, the sort of 4 to 4.5 billion years ago. And here I show a collection of 3 hypotheses, there are probably even more, about when SPA might form. Was it extremely early, like shortly after the moon formed? Which would be interesting, because then it would tell us that we actually have a relatively complete record of impacts on the moon. Is it in the middle here at the 4.3, which is kind of the current paradigm, I believe? Or is it somehow even later at 4.0 as part of the impact cataclysm? That would be really surprising. I don't think people expect that, but it's in the trade space. So really, to get this, you really want to get an age for SPA in order to pin these things down. So for all these reasons, SPA sample return has been one of the highest priority in every decadal survey that we've ever done. We just finished the third, but yet it has not happened. And one of the challenges is that geologic diversity of the basin. So here I'm showing that same view of the moon, and I'm on the left, you can see a lot of very small text of objectives for different missions. In this case, it's endurance, but if you were to look back at other missions to go to South Pole-Aitken Basin, the objectives would look pretty similar. And the problem is that in order to answer these questions, they drive you to different locations. So for example, if you want to date the basin itself, SPA proper, one place you might go, again, debated, but one place you might go is to the middle of the basin to look for impact melt. If you want to test the late heavy bombardment, you want to go to different locations. You want to go to those pre-Imbrium basins, things like Apollo, things like Point Care, and date those basins. If you want to look for mantle material or deeper material, then you might go to yet other locations. Here I'm showing high thorium anomalies. So this goes to some Dan Moriarty work suggesting that this might be deep mantle or a mantle adjacent material strewn onto the far side. And then always of importance is the volcanic history of the moon, which you can tie to the thermochemical evolution of the moon. And there are volcanic deposits across this basin. Here I'm just showing the Mare deposits in red. So these are younger deposits, but how did these form? How are they different from the near side Mare deposits? And yet again, different locations. So you can look at this sort of vomit-like diagram of the moon and realize there's no one place you would go and know with great confidence that you've gotten the right samples and the right in situ measurements to confidently address all the objectives. You might be able to do some, but it's hard to say you can do all of them. And so that's where endurance comes in. So the decadal survey, I had the privilege of serving on the Moon and Mercury panel for the decadal survey. The decadal survey is a huge task. It's a huge document, but it has a lot of work behind it. One of the goals of the decadal surveys are to prioritize new large missions for NASA, of which endurance was one. So here I'm just showing the Mercury and Moon panel, which was chaired by Tim Grove and Brett Denevi. And all these people are fantastic people. If you get the opportunity to chat with any of them, I highly encourage it. It was a pleasure working with them both in the decadal and on this concept. So as part of it, as I said, we had to look at mission concepts for the Moon and Mercury. And here's all the ones that we looked at. Many were from before the decadal. So there were a set of pre-decadal mission concepts done, including Intrepid, a long-range rover for the near side, Lunar Geophysical Network, in situ geochronology, and a Mercury lander. And during the decadal, we commissioned 2 additional studies from our panel, both for long-range rovers. One was Endurance, and another one was for it was called Inspire. It was sort of like a super Viper, where you would go through all the old cold PSRs on the moon. An important thing to note is these long-range rovers, really starting with Intrepid, were just game-changing. They opened up a new class of science that I don't think we had ever considered, at least in the decadal survey before. So the idea of being able to do these sorts of long campaigns, going to lots of different terrains, having a sustained presence on the moon opens up so much. And so there were a total of 5 rovers developed in this process, 2 from Intrepid, from Mark Robinson's project, 2 versions of Endurance, and this Inspire version. All these concept study reports are public. They're great, really thorough documents if you're interested in any of these. So going back to the map, when you take this capability and sort of design a traverse in order to do it, you end up building something like this. So this was a notional traverse that we developed in the report, where we would land in the middle of the basin, and you just drive to all these different terrains to collect samples and in situ measurements before eventually driving down to Artemis. And so Endurance A in particular was designed to rendezvous with Artemis in order to transfer samples and return them back to Earth. And that's shown here in our lovely cover art. We were very excited. HLS was selected during our concept study, so we of course had to stick a Starship in there. But this partnership between robots and humans is something that the Decadal really liked. I like thinking of Endurance as sort of an extension of Artemis, as something that can help the astronauts have a broader scientific reach than what they can do just by going to the South Pole. And so to give you a sense of scale, I'm actually going to click through all of these. For Artemis and also Apollo, we're used to EVAs sort of at a local scale. So Artemis 3, for example, might have astronauts walk within a 1 or 2 kilometer radius of the lander. So on the scale of, say, Washington, D.C., if your lander was at the Washington Monument, you could walk to NASA headquarters or almost walk to the Capitol. You could explore this region in great detail. If you add, say, a pressurized rover or several landers, you might imagine exploring something at the scale of, say, Shackleton or around Shackleton, which is sort of the scale of the DC Beltway. But Endurance is just a completely different scale. It is mapped to this. It's like driving from DC to Chicago on a route through the Appalachians off-road. It is just vastly different than anything we've ever done. And so why is that desirable? So not only do you get to collect samples from different locations, but that helps you mitigate some of the concerns associated with the bombardment process mixing up regolith on the surface of the moon. So imagine a traditional sample return mission where you land at a single site, collect samples, and leave. In that case, you're probably going to get a lot of material from that region, likely a lot of young material from that region, if you were to scoop regolith and maybe process regolith. And if you might be able to address science from that region, but if you want to have a broader implication for the rest of the basin, there you're relying on the impact process, the impact gardening and mixing of regolith to have delivered those special fragments from other basins around you, say from, if you landed in the middle of the basin and you want samples from the large Preambrium basins, you're trusting that they have delivered some small fraction of material to you. By traversing, the hope is that you cover and span this geologic diversity, and by collecting a lot of sample from a lot of different locations, you can start to disentangle this mixing in some way, whether it's some statistical approach or what have you. So this is one of the reasons that this long-range rover started to look really attractive compared to other concepts for returning samples from SPA. So here's the rover as it was designed in the Decadal survey. It was approximately a 500 kilogram rover, which is about half the mass of, say, Perseverance. It's still big. These wheels are about the same size as the Apollo LRV wheels, so that can help set a sense of scale. Doing this long traverse requires autonomy. It's not possible to joystick a rover on the far side of the moon and do this in a reasonable amount of time. Since we're on the far side, you have to go through a communications relay, you'll have limited windows. Things start building up on top of each other to make this untractable. Since we're on the far side, you have to communicate via a relay. So there's a lovely high gain antenna sticking off the back here. And in order to make the concept as simple as possible and be able to rendezvous at the South Pole, we baselined a RTG to power it. So we can drive it day and night. We can drive at the mid-latitudes where you have a nice proper day-night cycle, survive lunar night, no problem. Or we can even operate at the poles where you're worried about permanent shadow and sun having sort of irregular timing. Here's another view of the rover in a different position. So this had a nice long robotic arm with a scoop and sieve on the end to load up these sample boxes on the side of the rover. And here's a final one to give you another sense of scale. So this is actually a pretty big rover. You can see compared to this CAD rendition of a human being that looks a little creepy. So this is not a small rover. This is something in terms of footprint more comparable to the larger Mars rovers. So I think it's really exciting to think about this rover concept as a new way to explore, traveling a long distance, surviving a long time, and it's a different mindset to doing robotic exploration. For comparison, we baselined this rover to be able to collect up to 100 kilograms of material. So this is orders of magnitude more than what you can get from a traditional robotic only sample return mission. It puts us more in the category of things like Artemis and Apollo. And we're going just way further than any past rover, whether driven by an astronaut in the Apollo missions or a robotic rover on either Mars or Moon. There, the current record holder is Opportunity at 45 kilometers, and we're going substantially further than that. Oh, and this is a repeat. So needless to say, that's hard to do. So this level of autonomy is very challenging. And so to help contextualize it, I like to compare this between Earth and Moon. So on the top are a bunch of Google images of Earth at different scales, and on the bottom are Moon equivalent. So on Earth, if you're autonomous driving, you get in your Waymo. That Waymo has the virtue of being able to drive on roads that have been mapped and imaged. It is not dodging craters and boulders that have never been seen before. So on Earth, we have on roads centimeter scale images of basically every road in the United States. Whereas on the Moon, sorry, the best we have are LRO NAC images at maybe half a meter or a meter per pixel, which is about the same scale as the rover. So you're planning to a very different data set. And critically, if your rover gets stuck, if your autonomous car gets stuck on Earth, like here this autonomous car happened to drive into wet cement, you can send a person out to fix it, to pull it out of the cement. If you drive into an obstacle or do something to damage your vehicle, your autonomous vehicle, on the Moon, and there's no one around, you are stuck. That's the end of the mission. And so a classic example is Lunokhod 2, which got dust on its radiator, which ultimately caused the mission to stop working. So you have to plan your mission to be resilient, both given the available data and to potential obstacles. So the basic concept of operations, or CONOPS as we like to say, for this mission is that you would land this rover probably on a CLIPS lander or some CLIPS 2.0 lander, depart the lander and drive. This is a very long-range rover. The driving is the priority. Oftentimes we'll be driving hundreds of kilometers between sample sites. You might do science along the way, so-called traverse science. And so we baseline a lot of stops along the way, but it's really about getting to this smaller number, approximately 12 sample sites, where you do there you switch into a more ground in the loop operations to characterize that site, collect samples before repeating this process and eventually driving towards astronauts. So here's to show you just a segment of the traverse. The traverse, by the way, is in QuickMap and Moontrack if you want to look at it and play with it. Here's just a little subsection showing the Schrodinger Basin. The blue line is the Endurance Traverse. And so you can imagine driving along this traverse to two predefined sample sites that we pick from orbital data sets. You could imagine collecting all sorts of data sets along that traverse, things like continuous measurements, like from a magnetometer or from a particles and fields instrument, and then having regular stops every few kilometers where you take panorama and other in situ measurements. So I really get excited thinking about this future sort of noodle of high-res data that you would build up along the traverse. Endurance samples are currently baseline to be regolith samples, where you sieve them and pull out the rocklets. The rockets are really important for doing a lot of the geochronology investigations. But I'll note that this is an open trade that the science definition team will need to really revisit. One important thing for, especially since I'm here at JPL, one of the interesting things in developing this mission concept is comparing and contrasting the approaches between the moon and Mars. So obviously JPL has a lot of experience in roving on the Martian surface, and Perseverance, for example, is collecting samples as we speak from the surface of Mars to be returned back to Earth. And their sample collection system is extremely complex. It's a drill, it pulls out cores, it puts those cores in tubes. It is very complex and therefore also very expensive. So the hope is that we can leverage the geology of the moon to help us do this sampling for us. And so that's why we really like the idea of using sort of rakes or sieves to collect material out of the regolith in a little bit more simplified manner. And we also have the virtue of being able to deal with larger sample masses, so it's less critical to find that really small, perfect sample like you might have to do with a sample tube on Mars. So that was the endurance concept as designed in the decadal. The decadal recommended it for implementation. They gave us a lot of praise, which I copied and pasted here. And that was now several years ago. So where are we now? So the biggest thing that's happening literally right now is the science definition team for SPARCS, the South Pole-Aitken Basin Sample Return and Exploration mission. So NASA took these recommendations to do endurance very seriously, and they stood up this SCT to look at SPA science, define those objectives, look at a range of architectures, including the endurance rover concept, but not only that, and define these science requirements. So that way NASA can ultimately make a decision about how to implement this mission. So there's a QR code here if you want to look at the call. The call is now closed, but there's a lot of interesting information there. I'll skip this for the sake of time. Other developments that have happened is we had an endurance science workshop. So there's been a lot of work thinking about the science to be done. The traverses are now public. There's a QR code, or you can just go to, I personally like Quick Map. You can just go there, load up the traverse and look at it yourself. At JPL, we've been doing a lot of work in developing the traverse planning methodology. So how do you take these lunar data sets and plan to do a traverse at 2,000 kilometers, which is just such a huge distance given the limited data. We've also been working on the spacecraft and subsystem design. So this is what the rover looked like approximately now maybe a month ago. So it's noticeably different than what it looked like in the decadal survey. I can talk about design changes if people have questions. But one of the things that I get really excited about is we actually have been doing field demonstrations using new test beds. So the engineers have built this half-scale model of endurance, which they called Earnest. They like the Shackleton connection. And it's this all-wheel drive vehicle is letting us test a lot of the mobility options for the endurance architecture. So you can see here driving over rugged terrain and driving sideways. It can do all sorts of fun things. But the real challenge for endurance is the autonomy. So the Perseverance rover, and to a lesser extent Curiosity, do drive autonomously on the surface of Mars. Perseverance, I believe now, I forget the exact record that they've set, maybe drives hundreds of meters, maybe a kilometer autonomously. We have to dramatically increase that capability in order to be doing endurance, where you're driving much faster than Perseverance, about 10 times faster, and much further, about 100 times further. And so what I'm showing here is actually, in order to get this going as quickly as possible, we took the old MER, Spirit and Opportunity test bed called Athena, and put on the autonomy software that we've been developing for endurance. And so the rover, as it's been driving by here, is doing so autonomously. We put in a set of waypoints. We're just driving through the Arroyo here outside of JPL because it's something we have access to. And so as it's driving, it's autonomously surveying its surroundings using cameras and a LiDAR, detecting hazards, doing all the path planning, doing all the pose estimation, doing all the driving fully autonomously. And so this is an exciting demo. And even more excitingly, is because we're on the moon and operating at night, is we've now done this at night. So I'm going to show the next slide, which will have some strobing red lights. So if that is, if you're sensitive to that, please look away. But here is that rover, same rover, now strobing red LEDs, doing the same drive at night autonomously. So this is, and we actually exceeded our capability. We thought we'd have to drive a lot slower at night. Turns out we don't have to. And so this autonomous night driving capability will be really exciting for endurance. So this is my last slide. I know I'm rushing for the sake of time. But endurance is a concept for a long-range rover to do high-priority science across the South Pole-Aitken Basin, address these long-standing questions. It was recommended as the highest priority by NASA, and NASA, since the decadal, has, to its credit, done a good job at supporting this concept and moving it forward, both by funding JPL to do some of these tech developments in order to enable the mission, and by kicking off the science definition team, which will be critical in defining the actual requirements. Things like, what is the actual sample mass you really need in order to do these science investigations? Or what are the measurements that you need to take while you're on the surface in order to either contextualize samples or pick samples or characterize samples? So how to get involved? Well, first I'll note, endurance is, we are in the baby stages of mission formulation. For those that think about missions, we are in what we call pre-phase A. We have many years before this mission were to go to the moon. If it were to go to moon, it probably wouldn't be until the very early 2030s. So now is a great time to be thinking about the science that you could be doing in South Pole-Aitken Basin, potentially by a long-range rover. So thinking about those hypotheses and how you would test them, either with in-situ measurements or return samples, and getting those out into the community are really important, and they can feed into the STT, they can feed into the later development. And so I encourage you all to sort of put your thinking caps on and think forward to what you would like to see this mission do. And with that, I'll stop and take questions.
Thank you very much, James. And yeah, we'll open the floor up for any questions. And if you want, you can post it in the chat. Anybody here in person have any questions? Well, I guess Chip, go ahead.
Yeah. Hi, James. First, I wanted to thank you for giving this talk at the Planetary Sample Science Seminar series. I know there are an awful lot of people on campus and online really interested in this mission. The question I had for you, during the workshop, we had discussed the importance of getting large samples to do chronology and representative samples, but there's also, as we also discussed, a need for collecting fairly small samples, like, for example, pyroclastic deposits, where you have fairly small 100-micron volcanic beads. Is the sampling systems that are being considered, can they collect both types of samples?
Yeah, so I'll say what we're currently assuming. What we've currently been designing is a scoop that can both deliver unsieved regolith, which will be predominantly regolith fines, just because that's the way regolith works, but also a sieve in order to sieve out that sort of those centimeter-ish scale rocklets. So while the rocklets might drive the chronology, we have not lost the capability to collect regolith fines, things like pyroclastics. I do want to say that one of the challenges for this, and it's funny because Jack Schmidt was here talking about the importance of, say, large rocks like boulders and getting boulder chips and boulder fragments. One of the challenges is we have to balance the science needs with the technical and cost ramifications of them. So I feel very comfortable with scooping and sieving as a relatively simple, in quotes, and cost-effective approach. But I know that there's also a lot of interest in all sorts of more complex sampling mechanisms, like drilling into rocks or chipping rocks or doing like drive tubes. And so what will be really important in the next year or two is to think through what is the actual requirement? What could you not live without in order to do those science? Yeah.
Thank you, James. We have a question in the chat from Molly, who is asking why red LEDs for navigation during nighttime.
Yeah, so the red lights, so that was a decision by the mobility team. Basically, they wanted to look for they picked the red lights because the albedo of the moon is slightly more reflective in the red, so you get more of that bounce back, so it helps with the navigation. I don't think it's actually terribly dependent on the color, but that was fundamentally the choice was by the mobility folks. I thought that they'd get the better images with the red lights.
Thank you. And then we have a question from Lars.
Hey, James, that was really interesting. You know, I'm very big fan of all this. The thing I want to emphasize a little bit is that everybody bats around chronology like it's just like some joke and easy to do. And we're always fighting sample mass requirements. So if you go with a 1 centimeter size, material, which is a, half centimeter radius, you're at about a gram. Many rocks can't be dated at a gram.
Yeah.
You go to 2, you're about 10 grams, and you have a pretty good chance. Of course, it depends on the rock, and it depends on, what kind of system you're going to use. But right now, I think the general consensus is that one age on one rock doesn't really tell you much. You need to bring multiple chronometers to bear. And so I would encourage you to make sure that you don't just throw this around and such that you put too much emphasis on somebody making some miracle measurement, which isn't going to work out, because most of the chronology for a lot of the older things are just plain wrong, my own stuff included. And so give some serious thought to that, please.
Yeah, and I think that comment is well heard. It is. I've had some sprightly discussions with Barbara Cohen about this topic. And I think it's going to be one of the tall tent poles for the SDT to define, because it's clear that more is better in almost all regards. More in both in terms of total mass, the ranges of sample size, the types of lithologies you're grabbing, and figuring out that sort of sweet spot where you can balance that with the technical and cost ramifications of those decisions is going to be tricky. And ultimately, some of this is going to be beyond even the Sparks or Artemis or Endurance control, because if this is rendezvousing with astronauts, all of a sudden, it's actually not Endurance that sets a lot of the mass capabilities or requirements. It suddenly becomes Orion and HLS and these sorts of things. So that comment is well heard, and I look forward to the SCT thinking through that in the next few months.
Yeah, I know you have other questions here, but let me just close by saying there's a certain amount of luck involved.
Mm-hmm.
When you're doing field work, on the Earth, you usually collect a whole bunch of samples and you bring them back, and only a few of them are kind of the key samples, and you often don't recognize that in the field. And so I think you have to be prepared a little bit to either get lucky or unlucky.
Yeah, I think that was one of the things that helped us motivate that 100 kilograms mass, is hoping that you beat things down with statistics, aka luck. But now we have to back that up, And at some point, there will be a mass threshold where the community has to say, no, this isn't worth doing, and which will be an uncomfortable threshold to state, but 'tis the plight of mission development.
Thank you, Lars. We have another question in the chat from Michael, and he's asking, what are the plans for the rover once it arrives at Artemis Base Camp? Could be a nice complement to LTV autonomous operations to explore PSRs and etc.
Oh yeah, I get really excited thinking about extended missions, and to be fair, like every mission in formulation, you're not supposed to think about the thing you do after, because you've got to design to get the thing done in the primary mission. But if history has taught us anything, we tend to over design our spacecraft. We tend to make them more capable and more resilient than we necessarily needed to. And so one of the obvious things that this could do is, if it is RTG powered, we could do things like drive into PSRs. We could drive into the coldest PSR and sit there happily for however long you want. Now, our instruments and sample collection system may not be the right instruments to do, say, volatile science. But one of the things NASA did actually ask us to look at is thinking about swappable payloads. Like, do you want to plug and play a different instrument, like extended mission? So that's just one example. You can think of all sorts of fun additional traverses you could do, or ways that this rover could actually work with astronauts, like during EVAs, as sort of a follow along rover. So it's really up to your imagination at this point. With the same caveat I've been giving before, is we have to be careful about adding too many capabilities, like swappable instruments, that could have ramifications in the near term for cost. So, but we are notably different than LTV in a lot of ways. So it's interesting to think through how these things could operate together or simultaneously.
Thank you for the question, Michael. We have another question from James.
Hey, good talk again. Appreciate it. Just curious about I may have missed this. I had a slight distraction, but what is how does the payload get back to Earth?
Artemis. So
currently Artemis is only capable of bringing back like 50 kilograms or something.
Yep. So when we designed Endurance, the 100 kilograms actually came from me as a push on the engineering system. We wanted to design a rover that we knew would exceed the capability, or at least dramatically move us in one direction on the science. Now the current baseline is us rendezvousing with Artemis and delivering those samples to astronauts to return to Earth. And yes, at present, the current bottleneck in that system is believed to be Orion, which has a total return capability of about 100 kilograms, which includes the packaging and all the material that needs to enclose the samples. So the 100 kilograms does not fit within the current Orion box. There are a lot of ways you could imagine fitting the square peg into the round hole. Either the requirement is lower and you design Endurance to fit within the box. You could also imagine things like returning the sample over multiple Artemis missions, if they are actually happening at a regular cadence, or having the astronauts triage the samples or doing in situ analyses. But so much of that is uncertain that I think right now it behooves us to keep the sort of overcompensating science requirement, and we'll have to sort out what Artemis is doing later, since so much of Artemis is uncertain, especially in this time frame.
I really like that. Yeah, I like your original point about saying, okay, we're putting some stress on the system here by upping the requirement for the mass. And I think that's something that SDT really ought to push on, because that's a vestige. The Orion is a vestige of previous times when it wasn't even going to be returning samples. So I think that maybe Elon Musk will straighten all this out in the next few days, but we'll see. So thanks very much. Appreciate it.
Yeah, so we'll see. And one of the important things I skipped over in this talk was I mentioned that we did a bunch of rover concept studies, one of which was the fully robotic version. Let's say we didn't work with astronauts at all, and we just had a fully robotic system. And there you automatically drop down to something on the order of a few kilograms. So then you stress out all the sample science, and you add in $700 million for that second mission. So if we can make this partnership work with Artemis, it will be so exciting and valuable in so many different ways. So I hope that NASA can make that work in the future.
Yeah, I agree. Keep pushing on that because a gram per kilometer is not likely to be as productive as we would like. Put it mildly. Thanks.
Thank you, Jim. So one last question, and it will come from me. For those that want to submit ideas and stuff to the SDT, like where do we go for that input?
Oh, good question. So the SDT does not have a formal mechanism for ingesting external feedback. I mean, so the chair of the SDT is Lauren Josbiak. The SDT membership was just published. It was shared on the lunar list, I think, yesterday. Theoretically, there's nothing stopping you from contacting your friendly colleagues on the SCT. But honestly, the thing that I think is the most valuable is going to conferences, presenting your ideas, publishing those in papers, getting those ideas out and specifically framing them in terms of hypotheses that you could test is really valuable. That's one of the hardest parts of mission formulation is coming up with those requirements and saying, okay, 5 kilograms is okay, but 2 kilograms is not okay. And so having the scientific ammunition to know it's like, hey, if I need to do this geochronology type investigation, I actually need this kind of stuff from the moon, whatever that means, is really valuable. Otherwise, the SCT will have to do what they can with the available information. But if there are ways that you think that endurance or any, and this is really also true for really anything mission-wise, like it's true for Artemis as well. It's really valuable to, even if it's just a couple sections in the back of a discussion section talking about how your science ideas could be tested, that really makes a difference for missions in development. So yeah, my suggestion is give talks at LPSC, this AGU, DPS, GSA, those will be good times to sort of put stuff out there where they may get picked up by the SCT in sort of an organic way. And the SCT is not the end of the road either. They're defining requirements. They'll help move the mission forward. NASA then has to take that information, decide if and how they're going to do either endurance or whatever comes out of the Sparks SCT. It may not be a rover. It could be something completely different. But that's just the first step. Usually in these missions, then you have things like instrument proposals, instrument competitions, or science team competitions. So there's often multiple entry points into missions of this type. So just keep an eye on it and pay attention to lunar listserv. It's always fun to do.
Well, once again, thank you so much, James. That was a fantastic talk. And again, thank you guys, everybody, for staying. And please see you guys next week. Have a good one, James. Again, thank you so much.